like to introduce Dr. Anton Tremsin, originally from Russia, and then spent some time in my home country, the UK, at the University of Leicester, and he's now up at the Space Sciences Lab up on the hill. Again, if those of you who come to Cal Day, they do a great tour up there next April. I'm sure that they'll be showing people around the labs up there again. But Dr. Tremsin has kindly brought some of the work that he's been doing up there at Space Sciences Lab down here to campus to tell us about this morning, and he's going to tell us about the interesting new things that we can do with neutron imaging. So, thanks, Anton.
Thank you. Good morning. So I would like to tell you something about the work we do at Space Sciences Lab, but not our main kind of work, because of course Space Sciences Lab is mostly about astrophysics and instrumentation and measurements, but I'll tell you about something of our main path. I will be talking about neutron imaging. And the reason I present you this is because we had some technology which we developed for astrophysical instrumentation. And then we extended it to neutron imaging. And I would like to convince you that you can indeed see a flower for a granite wall. So the neutrons have very specific features and capabilities. So in the talk, I'll briefly explain you and compare neutron imaging with X-ray imaging, because these are two complementary techniques. And most of you, of course, are familiar with X-ray radiography, but not many know about how neutrons are used for imaging. And then talk about contrast in transmission images, sources which you would use for neutron imaging, and show you how we contributed to that field, and then show some applications of neutron imaging in different branches of science. So, of course, many of you are familiar with X-ray radiography, and that's the technology which is used for many years since discovery of X-ray by Röntgen. And X-rays can penetrate quite thick objects, and we're all familiar with the applications in medical imaging. So basically, you have a source somewhere and a detector, and an object is between source and detector. You measure the photons which are absorbed by the detector, and you obtain an image. And the soft tissue usually is quite transparent, and heavy Z elements are opaque. So what the contrast in X-ray imaging is provided by the difference in absorption of X-rays. And the same thing will be with neutrons, but we'll have very different contrast mechanism. So as is pointed out here, light elements like carbon, hydrogen, oxygen, which is consistency of most of our tissue, are quite transparent. But the heavy Z elements are opaque. So the heavier the element, the larger is absorption. And of course, X-rays are used in many other fields in addition to medical imaging, in non-destructive testing and in industry. And you can see inside of a particular connector, you can see the defects in that. Airplane turbines are inspected. So this is the technology which is well developed by now. One of the things where X-rays are used is in art, and the reason I mention this is because we use neutrons for art studies as well. So in that particular painting, you can see that the underlayer of the painting depicts that the man was in a hat, and there was no beard in it. But what you see on the surface now is this painting. So you have a means of non-destructively discovering what is underneath and how this painting was developed and painted, maybe altered at certain time. But in addition to just normal absorption contrast, there are many other techniques in X-ray imaging, which we'll also have for neutron. And in addition to just relying on absorption, basically you send a photon, it grows through the object, or it doesn't go, depending on the cross-section, and then you detect it with a detector. There are other techniques, and one of them is called dark field imaging, or refraction contrast imaging is another one, because there are some situations where absorption contrast is very low, like in that case when the heart is imaged in the right picture here. So if you just do an absorption image looks like this. There is not much of a structure because absorption coefficient doesn't change much. But what changes is the refraction coefficient or phase changes of the photon. And then they now can use a phase contrast imaging, which is a bit more challenging than just transmission. But we'll do the same thing with neutrons. Now, X-ray radiography and tomography, I'll mention tomography as well, is well developed by now. There are a lot of instruments, a lot of techniques are done. And sources are very bright, they exist around the world. They're lab sources, they're synchrotrons. They're very, very bright. So why would we add neutrons? And what neutrons bring to this field of imaging? And I'll try to show you what is unique with neutrons and why we use them. So first of all, neutrons and X-rays have completely different interaction with matter. So X-rays interact with electrons in the atom. As they propagate through the matter, they interact with electrons, and there's more electrons in a particular sample, there's more interaction, more absorption, more scattering, and so on. But neutrons don't interact with electrons. They interact with nucleus. And that's why the absorption contrast is very different for different materials. So what I'm showing here is a cross-section. So the diameter of each of those spheres proportional to the probability of neutron or X-ray to be absorbed. So the green ones are for X-rays and red for the neutrons. And as you can see, for hydrogen, for example, which is the lightest element, X-rays have almost no interaction because there's only one electron. But neutrons have the highest probability to absorb with hydrogen. And at the same time, look at iron, which is on the right-hand side. X-rays can interact with iron very heavily, very strongly, and get absorbed very easily or scattered. But the neutrons can penetrate iron, and quite thick amount of it, and still can see hydrogen within an iron cask. So one of the demonstration images, which was done in the beginning, they took a lead bucket and put flour inside of the lead bucket and imaged that flour within the lead bucket with neutrons. Of course, X-rays are completely blocked by lead. So that's why neutrons can bring you some new possibilities and can be additional techniques for studies where X-rays cannot be helpful. And other material, atoms like deuterium and oxygen, aluminum, silicon are shown here. So you can see it again. The contrast mechanism is very different, and neutrons can penetrate thick objects which X-rays cannot penetrate. Another demonstration of why neutrons can be very different from X-rays, you can see here there's attenuation coefficients. Attenuation equals both absorption and scattering. So there are 6 materials shown here: lead, copper, iron, polyethylene, water, and oil. So as you can see, the neutrons, again, the longer the bar, there's a larger probability to interact for neutrons with that particular material. So if you have, let's say, 1 centimeter of iron and 1 centimeter of polyethylene, neutrons will interact much stronger with polyethylene than with iron. So they will go for iron, but interact with polyethylene. And that's what's unique with neutrons. They can allow you imaging where you can look at the materials which cannot be imaged on any other way, non-destructively. So in neutron imaging, as an X-ray radiography, that's the same technique. You have a source. To be able to do imaging, you have to have a source of particles, of neutrons, and I'll briefly mention, of course, how we produce them. And then you place some collimation optics, because you have to have some sort of collimated beam for imaging, or a point source. But the point sources for neutrons are not easily available, so most of the time we use parallel beams. You put sample and then detector behind the sample, and then you look at the shadow. This is when you look at the absorption imaging. But there are other techniques like refraction imaging and phase contrast imaging where you use a little bit trickier setups.
Question, I don't know, a collimator is not in my vocabulary. I mean, could you say a word or two more about what a collimator is or does?
Right, I will mention that when I talk about sources, but briefly, the neutron sources, they create neutrons which are emitted in 4 pi in all directions. And if you have a beam which has neutrons which go in different angles, you place your object and the detector at some distance from the object. But because the beam diverges, your image will have some blurring. And to preserve the spatial resolution, if some neutrons come this way, from that point they reach this point of detector. The other neutrons came this way, and they produce image of the same point somewhere there, so you get blurring. That's why we have to collimate the beam and make it more or less parallel for neutron imaging, and especially if we do high spatial resolution. But I'll mention that more when we speak about sources. So as I mentioned to you, with neutrons, you can interact with hydrogen. So what unique things you can study is, one of them is you can look at the water distribution in wood, and you can study how water is absorbed by wood. Of course, wood is a big structural component of many buildings, and how it interacts with rain, and what is the speed of water absorption, and what is the speed of glue absorption when they use glue in wood. And you can visualize it with neutrons. So what I'm showing here is a set of images taken at the neutron beamline, and you can see how water is absorbed by wood in a certain amount of time. And only neutrons can reveal that non-destructively again. Of course, you can cut the wood and see where the water is, but then you destroy your sample. In that case, we can do it non-destructively. and in real time, more or less. And another area where neutrons are used is in archaeological studies or in our heritage studies. And what I want to show you just one of the examples from our colleagues in Switzerland, where they studied the bronze statue. And in that case, it's not just radiography, not just one projection image. It's multiple projections, which then they reconstructed into three-dimensional object, and then it's called neutron tomography, the same as X-ray tomography. But in that case, once you have a three-dimensional object, you can cut it, you can slice it in your virtual memory in the computer, and you can see what's inside, and that's what is demonstrated here. You can see, for example, that the blue is a hollow part of the sculpture. Without cutting it, you can tell what's going on inside. And X-rays wouldn't do it because they would not penetrate, but neutrons do penetrate. Now you can slice it, you can open it, you can look where the different materials are, how things were added at a later time, and that's what is exciting for archaeologists and scientists who work in this area. And a very interesting thing here is that we don't destroy the object. Of course, when we do measurements with very important objects from museums, it's very difficult to convince museum workers to give us sample, because we cannot bring our source to them. We have to bring sample to our sources. And I'll tell you how sources are produced. But once they bring it in, we have to take care that we have to make sure that these objects don't get activated. So I'll mention some difficulties of neutron imaging. But once you passed all of that, you can do studies like this. You can slice them open and look at different materials within them. And you can discover lead within bronze, and X-rays will not do that because they will not penetrate. So another object, which is of course very precious, this is 500 years old Buddha, and I wanted to study what is inside. Of course, this is an object which we cannot open, cannot cut, and since it was produced so many years ago, we don't really know how it was done and what is inside. And if we put an X-ray beam, in that case it's 150 kilovolt X-ray, which is very, very high energy X-rays, and the image you would see in the middle demonstrating what is inside, of course it will penetrate more or less this Buddha, because the energies are 150 kilovolt, it's very high energy photons. But then you don't see what is inside of it in terms of the things which neutrons can discover. And as you can see on the right hand side, the same object, put it in neutron beam, since metals don't interact that much with neutrons, but there are other things like wood, dry flowers, paper, they are revealed by neutron imaging. So again, these two techniques are completely complementary. And of course, if you can do studies with X-rays, it's much easier to do. You would do it with X-rays, but in some cases, neutrons allow you to see things which you cannot see with X-rays or other methods. And that's what allows scientists to see what's inside of this Buddha. This is another sample of a sculpture which again demonstrates what's the difference between neutron and X-ray imaging. And that on the right-hand side, we can see X-rays. Again, this is quite opaque object for X-rays. But on the left, you can see that neutrons reveal the different contrast in that object, and they can show where things were added at a later time. Because, for example, bronze composition changed as different centuries. There's different bronze composition, and you can tell differences and can see how that statue was worked on later on. Another very important field where neutrons are used is studies of plants and how plants uptake water. So people who give talks in this, and one of my colleagues, Dr. Kaiminati, he mentioned that this is one of the major problems, how we feed people. Of course, to feed people we need water, and water is scarce in many parts of the world. And if we understand and optimize how roots uptake water, then we can solve a lot of problems in the world, it looks like. So this group of scientists, they study how water is taken by the roots. Again, because neutrons can interact with water, and then that's what you can image with them by doing neutron radiography. And what they want to answer, of course, is how available is the water in soil to the plants, and how and where roots take water from soil, and how roots interact with the soil. And they try to stress plants, they put it in dry conditions, they put some fertilizers and see what happens. So the way they do the studies, they put plants in soil in these aluminum containers. And as I mentioned to you, aluminum is almost transparent to neutrons. Neutrons can easily penetrate through aluminum. And these plants grow for a certain amount of time. Once they've grown, they bring them to the neutron beam, and they can do imaging. So sometimes they go back and do repetitive imaging. And these are two examples of roots which were developed over 1 week and after a 4-week period of time. And as you can see in these images, the roots are quite well imaged. So you can see where the roots are, again, because neutrons interact with water, and they don't interact much with aluminum. So you can penetrate. This is in situ measurement, and you can study how the water is being absorbed. And how you can study the water absorption, I'll tell you a little bit more on this. So, as you know, there are different isotopes for hydrogen. There is hydrogen by itself, which is proton and electron. If you add neutron to a nucleus, it becomes deuterium. It's chemically more or less the same, but it has very different cross-sections for neutrons. So you can see two left spheres on the bottom image. The hydrogen has a relatively large cross-section, and deuterium has quite small cross-section. So if you make water, not with hydrogen atoms, but with deuterium atoms, then you can substitute one by the other, and you can see the front between two of them, because one of them absorbs neutrons heavier than the other water, the heavy water. And that's by doing this substitution, we can see the propagation of the front, where water is absorbed by roots. And this is the example of one of the studies where they looked at how water is absorbed by roots during day and during night. It's quite obvious, of course, the roots would be taking water during day because water is evaporated from the leaves. But then they want to see it in real experiments, and this is what is demonstrated here. So what they've done, they inject heavy water in the plant, and then the heavy water, since it absorbs less, once it's being transferred through the roots become but they're less absorbing because of a cross-section for deuterium. And as you can see on the left side, during the night, at 65-minute measurement, these plants didn't push that water into the main root. But on the right-hand side, you can see during daytime, the right side part of the image where they introduced heavy water, and the left side is where the heavy water was not introduced. This is the heavy water which was moved by the plant. So you can see it just moved through the roots up into the main root of the plant. So again, these are in situ studies, and you can study how water is being propagated by the roots from the soil to the plants. And that's something is unique neutrons can do. As I mentioned, also the neutrons interact with oil. They can go through metal and look where oil is in metal, and that can be used for studies of engines. And this is being done now. So, for example, if you want to look at the oil distribution within an engine, and of course, in that case, we use usually small engines, not really big ones. But then you still can study whether oil is in the engine, if lubrication is correct or not. And this is something, again, unique, which X-rays cannot do because they will not show the oil. And on the other hand, you can also sense explosives. Again, this is kind of scientifically driven applications, not for homeland security or other applications where you sense explosives, because they cannot bring neutrons to many places and they're harmful. But once you need to study something, this image just demonstrates, you can see the gunpowder within the bullet. So neutrons penetrate metal and they interact with gunpowder, which is organic. And other instruments and airbag sensors can be sensed as well. And these are tomographies. So in that case, our colleagues studied engine, and they did study in a stroboscopic mode. So in that case, they took an engine, which is a full block engine, aluminum block engine, and then the middle picture shows the engine being static. So the oil pipes are not filled with oil. This engine has not been run. But on the right-hand side, you can see the image, and you can see some of the oil being spilled to, oops. You can see oil in the pipe, so you can see this oil blob which goes into the piston. So you can, in real time, in a running engine, observe where oil is distributed and see it within the metal block, which is aluminum engine block. Again, because aluminum is very transparent to neutrons. This is something unique, and you can do stuff. But these are just unique studies. You won't do it on every engine. Another area where neutrons are widely used now is studies of concrete. Again, my colleagues who are working in this area, and Professor Whitman in Germany is one of the experts in the field, gave a talk recently, and used some slides from his talk, that the amount of money was spent on structures and to fixing concrete and rebuilding things is enormous. So if we can extend the life of concrete, it will be very beneficial economically. And the mechanism of concrete damage is through several mechanisms. Of course, ice cracks in the concrete, and then salt, which propagates into the concrete, then reaches the iron bars and then destroys the protective layers. But again, how you can study this non-destructively, neutrons may be very helpful here. So you can look how water propagates through different concrete mixtures. And these are 5 images shown here that they demonstrate how water is being sucked by the capillary forces into concrete. And that you can see where the front of water is, and you quantitatively measure how much water is in your concrete and how long it takes to propagate and so on. And you can look at salt in concrete. And one of the other studies they've done, they actually developed a crack in concrete intentionally. And the way they've done the crack, they put a load, if you can see on the image here, they put the load on a concrete bar. They created a crack here, and then they put that crack into a place where there was water at the bottom. And as a function of time, you can see there's 2 projections. One of them is horizontal, and the other one is vertical. And you can see in these 2 projections, quantitatively, they can measure where the water is around that crack, how much of it, and how soon it goes to which position. And of course, when this water reaches these metal bars, the steel bars, the steel protection layer gets stripped off, and that's a mechanism for the failure for the concrete. So concrete studies is one of the areas where neutrons are used. Now, I told you good things about neutron imaging, why they are useful, and now I should tell the difficulties of that, because neutrons are not as easy to produce as X-rays. They're quite harmful, and the reason we're not using them very frequently, and at least I, 5-6 years ago, didn't know much about neutron imaging, because they're very rare, so very unique studies. So neutrons are dangerous to any life because they can cause a lot of damage, so you don't want to be next to a neutron source when neutrons are running. It can also activate materials, so you can put some material in the beam, and that material gets activated, so it becomes radioactive. Once you activate it, you cannot take it away from the source. Some materials do, not all of them. The facilities which create neutron beams are quite expensive. And then compared to X-rays, the sources of neutrons are quite weak. They're 10 orders of magnitude less bright. And how do we create neutron beams? So if you want to do imaging, of course you need beam of particles which penetrate through your object, and then you detect it with a detector. There are 2 ways of creating neutrons, 2 major ways. There are also portable sources, but they're not useful for imaging. So one of them is, of course, nuclear reactors, research reactors. And in that case, we create neutrons just in the nuclear reactor. Then we collimate it with the optics, meaning we just reject the ones which go in the wrong direction. We only leave neutrons which go towards our detector. We place an object and then the detector behind it. So these beams are run continuously. There are quite a few research reactors in the world, but very small amount compared to X-ray sources, of course. But the other way of producing neutrons is through spallation. And I'll tell you a little bit more on this. In spallation, what you do, you hit a proton beam into a target, into some nucleus. And that proton beam is very high intensity beam, very high energy protons. They're accelerated in a big accelerator facility to 90% of speed of light. So this is a very high energy protons hitting nucleus, and nucleus basically just is ripped apart, and neutrons are emitted in all directions again. So in the case of spallation sources, we can create pulses of neutron beams. So once they are pulsed, there are very interesting things we can do with pulsed sources compared to continuous sources. And these pulses would be in the scale of 30 to 100 microsecond in duration, and they would run at 50 to 60 hertz repetition rate. So on the left there is an image of a nuclear reactor pool. This is where you see this chunk of light, blue light there. And on the right, this is just a few photographs of an accelerator-based facility where we do spallation of neutrons in spallation sources. So what happens when the protons hit this mercury target, which is shown here by an arrow. So that mercury is flown here, and that target is the proton beam hits on the red point here, and the neutrons are created and go in all 4 directions. And these neutrons, which are created here and in nuclear reactors, they are usually high energy neutrons. So if we want to do imaging, we really need to cool them down. So from kilo-electron or mega-electron volt energies, we need to go to milli-electron volts. And the way we cool neutrons is through interaction of neutrons with water or liquid hydrogen even. So neutrons, they're like billiard balls. They interact with hydrogen atoms, they lose their energy, and by the time they get many interactions, they become low energy. And this is mostly neutron studies done with neutrons which are thermal and cold energies. not high energies. But these are two main techniques which we would use to create neutrons. So as you can see, these are very unique facilities. Not many of them exist, and that's why the neutron studies are quite rare. Now I'll switch to our contribution to this field. So you might think, okay, we talk about neutrons. What Berkeley is doing in that area? And I'll tell you how we get involved in this. So we, in our group, work on developing detectors for astrophysical applications, for synchrotrons, for bioimaging. And these detectors, again, are not replacing every other detectors. They have their niche. Devices which we build, they detect single particle at a time. And that particle can be photon, electron, ion, and since recently, neutrons as well. So we detect one particle at a time, and we find position and time of every particle. And from that, we can build images, of course. So one of the instruments which we built in our group is launched on image satellite quite a few years ago. I just show you that this is technology which we worked on. And as you can see, this satellite was observing Earth aurora, interaction of solar wind with magnetic field of Earth. And this is the image taken with our detector, which was launched on image satellite, which is on polar orbit. And you can see the development of the aurora around the North Pole. And this shows the dates when it was measured. And the set of images on the top as well shows how the aurora develops in time, taken by that satellite. And I'll tell you how this technology works. Another detector we built, we're proud of it, was installed by a last servicing mission on Hubble telescope. It's called Cosmic Origin Spectrograph. And we're very proud.
What was it called?
Cosmic Origin Spectrograph.
Cosmic Origin.
Spectrograph, COS. There were two instruments installed and other electronics fixed, but one of the instruments was our, and I'll show you the picture of the detector. So the detectors which were built, they're used in different areas, different fields of science and engineering. And of course, since they're event counting, they can be used for mass spectroscopy and astrophysics. We do synchrotron instrumentation here at Berkeley Lab as well. We do a lot of biomedical research. So from looking to stars, we look at very small cells as well. And this one image on the right is showing the image of a cell. I'll mention that briefly as well. Because in that case, since we're measuring time of every photon, we can do fluorescence lifetime studies. And this is very exciting for us as well. We're collaborating with our colleagues from University of Los Angeles, University of California at Los Angeles. And since recently, we use those devices for neutrons as well. So the detector, which I'll show you data we've taken with, was built for, originally was built for adaptive optics applications. This is another area where channel plate detectors, which we built in our lab, can be useful. And I will not spend much time here, but if you can use adaptive optics, you can get resolution comparable to Hubble telescope, but from the ground. The trouble from the ground astronomy is that there's turbulence in atmosphere, which makes the object blurry. But if you have ability to measure this turbulence and provide information to the mirrors, which can correct for it, then you can recover the unperturbed wavefront and get very good images with high resolution images. So what we've done here, we were working on a detector which would allow us to measure the turbulence of atmosphere with frequency of about 1 kilohertz. So what we needed here is a sensor which will allow us to measure the position of every single dot. And as you can see here, for unperturbed wavefront, these dots are in a regular grid pattern. But once the turbulence in atmosphere changes it, these dots move. So if you can measure how far they moved from the center, and you can send this information to the segment of a mirror, which will then move by the same to correct for that perturbation, then you can get unperturbed wavefront. So that's what we're building. You have to have very high frequency, very high resolution detector for this. But then we transferred the technology to neutron imaging. And as I mentioned to you, one of the areas where we built detectors for was fluorescence imaging within live cells. So we're looking here at the fluorescence. So the scientists excite live cell with a laser, and then they measure how much time it takes for the photon to be re-emitted from that laser pulse. And the resolution here, we need to measure photon, every single photon, of course with some efficiency. We don't detect every single photon which is emitted. Our efficiency is on a scale of 30% only, but we need to measure with accuracy of 100 picosecond. So that's a very, very high timing accuracy for photons. And then we can provide both position and time, and that's why it allows us to do this fluorescence curve for the entire cell, not just for the point. So I showed you how we've done imaging in astrophysics and biological imaging, but how do we extend it to neutrons? So most of the technology which we develop here with very small change is applicable to neutron imaging, and I'll tell you how we do it. So detectors we built, they are based on microchannel plate, and microchannel plates are made from glass. So imagine this disk, which is not to scale. The disk would be kind of a couple of inches or 1 inch in diameter, and we have many, many holes. So these holes are 10 micrometers, 1/5 of the human hair. It can be as small as 2 micrometers. So a disk of this size would have 10 million holes. And each of those holes functions as a secondary electron multiplier. So if you look just at one pore, which is shown on the right, in that pore we have one electron at the top. We have electric field from top to the bottom. This electron is accelerated, hits the wall, creates 2 electrons, and 2 electrons hit the wall, create 4, and so on. And then we start with 1 electron, we end up at the bottom with multiple electrons, 1,000 to 1,000,000. So we start with very weak signal of 1 electron. It's very hard to detect 1 electron electronically because electronics noise kills you. But once you get 1,000 to 1,000,000 electrons, you can very easily detect them. That's the technology we use. So we use channel plates which amplify our signal, and then we detect with different electronics. Now, how we convert this signal into position? So behind this channel plate, we can have 1 or 2 channel plates. Again, they're very thin disks, 400 micron to a millimeter in thickness. We place different readouts at the bottom, and these readouts, they can be different types and have some advantages and disadvantages, of course. But what's nice about this technology, we have no readout noise. CCDs have readout noise because of the nature of the build. But since we amplify signal to 1,000 to 1,000,000, we have no readout noise at all. So we get 1 particle coming in, we detect 1 particle. And we can tell both position and time with 20 micron accuracy and 100 picosecond timing resolution. And of course, we can detect electron ions because once they hit the channel plate, they create secondary electron, and these secondary electrons, we amplify them. Photons create photoelectrons. Now, how do we detect neutrons? So for neutrons, there was a very small change from the technology we worked on, and the change came from the idea which originated from England. The idea was to dope the glass with material which absorbs neutrons. In that case, it's boron-10 isotope. And that isotope interacts with neutrons. It creates 2 particles which go from this wall and hit the adjacent pores. And from that point on, they create electrons and amplify them. So from that point on, detection is just the same as what we've done for photon imaging. So basically, just changing composition of the glass. And there's a company we work with, Nova Scientific, who does these channel plates now. They changed the composition, added boron-10 into glass. Now we are sensitive to neutrons. And in fact, we're very sensitive. We get efficiency of 70% to cold neutrons, which is very unique for the neutron field. And at the same time, the event happens just within the single pore. So this pore, which is shown here, is again on a scale of few micrometers, 10 micrometers. So the event stays within 10 microns. It doesn't go anywhere sideways like in scintillator, where light spreads out. So we place this channel plate, which are neutron-sensitive channel plate above a particular sensor. In that case, I'll show you results we obtained with TimePix chip, which is a chip which is developed by CERN collaboration. And that chip has a lot of pixels which are running almost independently of each other. They can run at 100 kilohertz speed rates for every pixel. We placed our channel plate above it, and then we place it in a vacuum container. Detectors we built, they require vacuum. The microchannel plates, they need vacuum for operation. And then we place it in the neutron beam, and these are the first images we've taken. So I'll tell you a little bit about tomography. Maybe some of you are not familiar with it. How you get a three-dimensional object from a radiography. Of course, radiography gives you the projection. So basically a transmission of objects. So you get line of sight and the transmission for line of sight. But how do you get the three-dimensional information from it? The images of sculptures I showed you, for example. How do you get three-dimensional image? And the idea here is you take multiple projections. So you take an object, you take a projection in this angle, and then you rotate it, take another projection, and you do multiples. In that case, I'll show you 180 projections we've done. And from 180 projections, you can mathematically reconstruct the absorption of every voxel in your object. Once you get absorption of every voxel in your object, meaning tiny small volume, then you can get a three-dimensional object. So here on the right is a tomographic reconstruction of the data which is shown in the middle. And that's a small object. So what we bring to the field of neutron imaging, of course there are other detectors, and they're very widely and well used based on CCD technology. But what we bring it into the field is a possibility to count neutrons, and I'll tell you why we want to count them and measure time, and we'll get high spatial resolution. So the object, the same one that's shown on the left, is just a nut with a plastic zip tie. But you can see here, you can now separate them because they have different absorption coefficients. Mathematically, you have these objects in your memory. You can separate them because you tell, okay, this is object of this absorption, this object of this absorption. Virtually, you can do whatever you want of them. So it's, again, non-destructive way of studying things. You can go inside, you can zoom in. So we just demonstrate here with a simple object that the power you have from tomography, of course, the penalty, you have to take multiple projections. And usually neutrons, because neutron radiographies are quite slow compared to X-rays. In X-rays, you can get data like this for three-dimensional in a second. For neutrons, we actually spend much longer time to get good statistics because our sources are quite weak. But then you get three-dimensional object and you can do whatever you want with it. So here are the examples we've done with our detector. Again, we're bringing in high resolution possibility to image neutrons. And as you can see, this image of a flower, it's of a fly. It's a very good Swiss fly. It's not as small as ours, but that allows us to study a fly, and we can probably see some different tissues. For example, behind the fly's eye, we can see nerve cells, we think. So we're trying to investigate what contrast mechanism can be done here. So if you do an image of the same fly with X-rays, it will be much higher spatial resolution, but the contrast mechanisms are different. So we're trying to find out niches where neutron imaging would be much better and gives us unique information which X-rays cannot provide. And as you can see on the left again, you can see the organic powder within the metal casing with quite high resolution because neutrons are not stopped by the casing itself. So these are just tomographic studies. In addition to tomographies, because our detectors are really fast, as I mentioned, we do counting, but at the same time we can do multiple particles which are amplified by the channel plate, and then we can image them. So we can do stroboscopic imaging. So if you have objects which are really fast, changing in time, and in that case, we just demonstrated, for example, a spinning fan, a computer fan, and we place two objects on it, one the cross and the square. These are the objects which are made of cadmium, which absorb neutrons quite well. So if you do static image, you can see that the image is here, and you can do it very easily, of course, just static. But if you start spinning the fan, so what we can do, we can time tag every neutron we detected. Now we can tell, okay, group images to the position where they correspond to a particular phase of the fan spinning. And as you can see here on the right, so these are the images which we've taken for different phases of the fan. So the fan is rotating at 50 Hertz, but we can still image it as if it's stationary, and we can see different phases by doing stroboscopic imaging. So another thing we demonstrated, you can, again, study water in real time, and water in pipes, for example. And in that case, we have water from a bottle going down through a pipe. You cannot see it very well on the left, but here is aluminum pipe on the left bottom of the photograph, installed in front of our detector. And what we're doing, we're putting water and air bubbles in that water through the pipe, and we can image it in real time. And again, how we can see water within metal pipe by other techniques, non-destructively, that's probably a very unique capability of neutrons. So we can look at distribution and dynamics of water. Another thing we tried to study was distribution of oil in the fuel injection nozzle for a diesel car. Because again, people can look at oil distribution within the engine block. They can drill the block, put the camera, and see how oil is spread out from the injection nozzle. But if we can optimize that process and find a better way of doing injection nozzles, because sometimes this fan is not uniform. There's some turbulence happens inside of some cavitation happens within the injection nozzle, and oil is not uniform as it's spread out. So if we can see inside of the nozzle what happens inside, what causes these non-uniformities, then we can improve the operation of the fuel injection nozzle. And for that, we need to penetrate metal and still see oil in it. And these images show here that in principle, we can do it. So you see these oil channels where the oil is propagated through the injection nozzle. And at the top, there is a valve which opens and closes multiple times per minute. And we can image that. So we've done dynamic studies. Again, we need more statistics. But you can see, again, very poor statistics yet. But we can see how the spread comes out and what happens within the nozzle. So these studies will be continued. Another thing we can do is look at the soot deposition. And this is the pressure sensor for a diesel engine. And with X-rays, you wouldn't be able to see it again, non-destructively, because they will not penetrate metal. But in that case, with neutrons, we can penetrate it. We can see where the soot is deposited. And that allows us to do studies non-destructively. Another just demonstration experiment, we saw how water is being pushed by capillary forces, and you can see how a napkin sucks up the water from a water container in real time again. So for that, we need a lot of Newton statistics, and of course, the sources are not very bright, so you can see kind of grainy images, but they're still showing up where the water is. Now, I mentioned to you that pulse sources are unique because they allow us to do pulse neutrons. And one thing I didn't mention yet, of course, the time of flight technique, which we use for measurement of neutron spectroscopy, I'll mention a few words here about this. So why do we want to do measurements of transmission as a function of time? So neutrons, they don't fly as fast as speed of light, of course. So if we can measure the time of flight...
Sorry, they don't move as fast as what?
Not move as fast as speed of light. So thermal energy neutrons, by the time the pulse is produced, they reach our detector, it takes from millisecond to, of course, microseconds to milliseconds. So if we can time tag every neutron, we can measure energy of the neutron. And I'll tell you why we want to measure energy of the neutrons which went through the sample. And one of the applications is to measure strain in materials. So of course, we're all familiar with the Bay Bridge accident we had when they get the eye bar crack. So the cracks are being formed because there are stresses in engineering materials, and stresses, they increase the probability of crack formation. And we can do studies with neutrons within the metals where the stresses are distributed and actually optimize the engineering structures, how we can increase the durability of elements. Of course, we cannot do it on a bridge. We have to do a kind of fundamental studies and invent new materials, but then we can still use that knowledge when we build real engineering objects. So here I'm showing the transmission as a function of neutron wavelength in the thermal range. So on the bottom we can see neutron wavelengths, and on the left side you can see the cross-section of neutrons absorption. So as you can see, for different materials, for crystal materials of course, for different materials, hydrogen will not have it, but crystal materials have very sharp edges. As neutrons change the energy, the transmission of metals changes by a large amount sometimes. And the position of those, we call them Bragg edges. And the position of these Bragg edges is proportional to the crystal lattice parameters. So if you pick up, let's say, the blue curve is a nickel, you can see at energy of 4 angstrom, there's a very sharp change in transmission. So if you take an image before 4 angstrom, it'll be quite absorbing. And if you go past 4 angstrom, the object becomes quite transparent. So by doing time tagging neutrons, we can now, since we're detecting neutrons with time and position, we can do energy resolved imaging. So it's not just in transmission in general. It's also transmission which depends on energy. So instead of measuring one image, we measure multiple images for different energies. And once we measure them, we can determine where the Bragg edges are. And if we know position of Bragg edge, we can tell what is the strain distribution within the sample.
What is the term cold?
Cold neutrons, the neutrons, again, they have different energies. Because photons, they have different energies as well. X-rays, they're high energy. Visible light is low energy. The same with neutrons. Cold neutrons and neutrons which are with energy of about 5 milli-electron volts, thermal are 25. So they travel with speed of 2 millimeters per microsecond, approximately. So, and the thermal neutrons correspond to energy of wavelengths of a few angstroms, and thermal to 1 angstrom. So again, energy dependent. This is the term, the kind of broad term. The cold neutrons are neutrons which are with an energy of about 5 milli-electron volts. So now if you take an object which is iron and copper, and you measure transmission of that object, so in different areas, I'll show you squares of copper and iron, and you can see different color curves, the blue and the brown. The brown is copper, blue is iron. So you can see the transmission of these materials is very different. So instead of this image, which is kind of gray image at the top, you can now get images which would be energy dependent. And if you look in the area 1, the gray area highlighted in this graph, the iron is not absorbing much, but copper is absorbing. And in area 2 is vice versa. Iron absorbing, copper is not. So what you can do now, you can get the same object, but the image is black and white, white and black. So just having energy resolved imaging, you can do material dependent studies, see where different materials are, but more important, you can measure position of this Bragg gauge, and from that position you can tell the strain distribution within the sample. Because with our detectors, we're detecting time and position. Again, that's a unique thing. with high spatial resolution, and then we can tell in a particular pixel of our image what is the spectrum of transmission. And once we know the spectrum of transmission, we can recover the Bragg edge position. And from that, it's a little bit complicated maybe, but from that we can reconstruct the strain distribution. Basically, if you have a metal bar, if you try to bend it, there are strains which are developed within the bar. And of course, at some point, it will just give up, maybe crack or just yield. And if we can measure distribution of the strain in engineering samples, we can tell how the material is behaving, what is the structure there. And one of the cases with studies here is they try to look at crack propagation in metals. So what they've done here, they have these metal samples. These are steel, and they put them in the vise, and they try to pull them out multiple times. And the crack grows between these two holes. And you can see this red square. We looked at the distribution of strains around that crack. And as you can see here, the strain is, of course, the high concentration of strain just around the tip of the crack. And then it changes as it propagates. But now we can quantitatively measure the strain distribution. And that's something unique with neutrons. Because with X-rays, you can do these studies, but only on thin samples. For thick metals, neutrons are unique. And this is one of the examples how we do the measurements. You can see on the left side, there is a vise where we pull metals apart, and then we can see how strain is developing in it. And we can do studies of this Bragg edge position. So you can see the transmission of the steel is changing dramatically. There are sharp edges, how things are changing in transmission. This is another example, just bent bar. And you can see the strain concentration within that bar, again, with high spatial resolution. Yes, question, please.
Why does the stress affect the neutron absorption?
That's a good question. These edge positions, which I showed you, they are proportional to the crystal lattice parameter. So if I measure for unstressed sample, my edge position will be in a particular area. It's proportional to the distance between atoms in the crystal. Now, if I put stress in, the atoms get moved further away apart or move closer, the edge position changes. And it changes by tiny amount, but this amount is actually very challenging to measure. They're changing by milliangstrom. So the wavelength would be, let's say, 3 angstroms, and it changes by milliangstrom. But if we can measure that accurately, and we can find out what is the strain in that particular point. And of course, for that, we need to know sample unstrained first, and then we measure strained ones. And the challenge here is that with what we measure, the source itself is broad enough in the beginning, so we're not getting milliangstrom accuracy, but we do mathematical tricks by doing fitting, and we can recover our data, reconstruct data with milliangstrom accuracies. Another application where we use our detector is in fuel cell studies. So a few years ago, there was a lot of promise for the cars to be powered by fuel cells. Of course, it's not happening now, but this research is still being done. And in the fuel cell, there is a membrane where there's exchange of water, of electron and oxygen happens. So in that case, we want to look at this very small area within the fuel cell. So we need very high resolution because this is the area of interest. These channels where the water vapor is being flushed away from the fuel cell. And if they get flooded with water, then the battery stops operating. Again, neutrons are very powerful here because they can look at water distribution within the running, functioning cell without any perturbation to the cell itself. And we just demonstrate here we can get very high resolution. And by the way, you can see here the screw, and it has very funny structure with white and black lines. So this is the refraction on the screw threads, which I did mention a lot about refraction imaging. But in addition to just, since the talk is about neutron imaging, to just normal absorption, there are other mechanisms similar to X-rays. We're following what was done in X-rays. There are other mechanisms where you can get image, contrast in your image. And the refraction mechanism is one of them. So there's phase contrast imaging, refraction imaging. These are techniques which are being developed, but they are trickier and harder to implement. So one other unique thing with neutrons, which I didn't mention yet, neutrons have spin, and spin interacts with magnetic field. So if you have a magnetic field, you put neutrons through it, the spin of neutrons will precess. And we have a technique now which allows us to measure the magnetic field distribution, basically get an image of the magnetic field as it is shown here around the magnet. And this is done non-destructive. So this is, if you cannot put your magnetic probe in some area, but you can use a neutron imaging technique to demonstrate and quantitatively measure magnetic field distribution. So this work was done by our colleagues in Berlin, and we followed that work because we do timing in addition to position. So what we've done, we looked at a magnetic field which is changing in time. 3,000 times per second it changes its amplitude. So it's AC 3 kilohertz magnetic field around a coil. And as we can see, the image is kind of blurry, but because there's not much statistics, in that case, the challenge is we'll have to create a neutron beam which is polarized, spin polarized. And then we'll have to get analyzer, which also cuts our sensitivity. So, but in that case, we can see the development. This is a 300 microsecond duration movie. So we've taken multiple exposures, of course, to get that movie. But that's something challenging. So if, in theory, what we should have measured is something like this. For different neutron wavelengths, we will have different interaction, different spin per session. Since we're measuring the kind of polychromatic beam, all these combined together, that again, I wouldn't go into details, but something to demonstrate here. We can measure magnetic fields with neutrons, and not just measure, but get images of magnetic fields. Another thing I'll mention briefly is resonance absorption imaging. So far, I've been talking about neutrons of thermal and cold energies. But there are, of course, in the spallation source or in the nuclear reactor, for that we would need a spallation source. The neutrons are produced of all energies. So if we use neutrons which are kind of high in energy, so the electron volt type energies to a kilo electron volt. What they have, neutrons, they have very sharp absorption probability at certain energies. So in that case, what we can do, we can study different isotope distribution within materials. And in that image we're showing here is a belt buckle, which was a replica of an ancient belt buckle. And of course, there is bronze, there are different silver parts in it. So what you can see here is a movie. It's a slice through time, time of flight basically, or these slices correspond to different neutron energies. And at a certain time, like it is coming up now, you will see this black thing showing up, like this, they start flashing, this black. These black pieces are made from silver, like this now. So at a certain neutron energy, silver absorbs neutron beam, and we can tell exactly which material, even which isotope of a material is in a particular pixel of our detector. And for that, we need very high timing resolution. So again, non-destructively, you can sense different isotopes within your sample. And for this method, we don't need much of a material. So for silver, for example, we can see 20 micrometers of silver within centimeter thick object. And not, of course, all materials have resonances, but quite a few of them do. And as you can see here, instead of just an image which would be a transmission image shown on the left, we can now get an image which is very specific to a particular isotope. So if we just take an energy slice where there's a resonance for a particular isotope, we can see it within object, and that's done non-destructively. And another thing we can do with this resonance absorption is we can measure temperature. Again, non-destructively. So these are experiments I'll show you here. Is this for a particular material, in that case it's tantalum, we get these very deep resonances, resonance absorption at certain energies. And these energies are unique for different isotopes. But what happens if we warm up the sample, the material, this resonance due to Doppler broadening become broader. And if we quantitatively measure the broadening of it, we can tell what's the temperature of the sample. So not only we can tell which materials exist there, we can also tell what are the temperatures there by doing this technique. So this is something unique with neutrons. And of course, all my work was done with a lot of collaboration. We've been very lucky to get to many different neutron sources and learn and work with all our colleagues. This is very good community of people who helped us to develop this technology and get all these results which I demonstrated today. And I would like to finish with this picture which was taken at the Paul Scherrer Institute of a flower behind a granite wall, again, because neutrons can penetrate granite, and they can see flower behind it. Thank you, and we'll be glad to answer questions. Please, please.
I was curious, you're pretty previous slide you were indicating that magnetic field with neutrons, which surprises me since neutrons have no charge, right?
Exactly. Neutrons are neutral particles, but they have spin. So if neutron beam is polarized, so only neutrons with particular spin coming in, the spin, if it sees magnetic field, it starts precessing. And then what we do here is we polarize the beam first, as it's shown on the left. So in that case, we lose at least half of the intensity. Half of the neutrons are taken out. Of course, we lose more. And then the spin of the neutron precesses. And then we put analyzer behind. And if spin is aligned with analyzer, it's transmitted. But if it precesses, it gets no transmission. So by measuring the gray value at the image, we can see how fast the neutron precessed. And that allows us to find out what is the value of the magnetic field. So this precession will be proportional to the amplitude of the magnetic field and the time neutron spends in it. So there's two parameters. That's why we need monochromatic beam, ideally, to study the precession precisely. Yes, please.
I had a question very early on when you were talking about refining the focus in the astronomy examples where you get the blurring, and that you can actually measure how much off-center something is moved, and then you could do a feedback. But isn't there a delay in that, so that by the time the feedback, the measurement of the displacement is displaced to a new place?
That's a very good point. The feedback should be really quick. I'll try to find it.
So it's a question of the ratios of the...
This process should happen within, I guess I passed it. This should happen within a millisecond. So that's why it was challenging to build this sensor for us. I mean, other sensors exist. So you have to be able to measure it within a millisecond and move the mirror within a millisecond. So that feedback should be very fast. Otherwise, you're too late, of course.
Yes.
So the turbulence likely is on the scale of a kilohertz. So if you're able to measure it and then move your mirror within a millisecond, then you're catching up fast enough, yes. And then you can get much better imaging, of course. And as we've demonstrated.
How fast can they move these mirrors?
They move with a kilohertz speed.
Yeah, that was the one.
And then from the global image on here of a star, because of the atmospheric vibrations, you can get something really sharp like this. So that's amazing technology. Yes, please.
You mentioned a number of materials. I was curious about how transparent glass, Pyrex lab glass, and nickel and palladium.
So glass is quite transparent. It's silicon and oxygen, so they are not absorbing too much. So we can go for quite thick glass. Nickel, I have to look into that. I guess nickel, depending again on energy, what is you trying to image. I think nickel has nice dark edges. And it has some absorption, but depending on what you want to study, we can discuss that and see if we can go to epithermal range maybe, or thermal range, and see if we can get transparent enough. I don't know much about palladium. I have to look at the absorption cross-section or scattering cross-section. Yes, please.
Yeah, I just have a question about the spin. So when you describe the spin, is it actually something like the neutron is a sphere that's spinning like a soccer ball or something?
Not really. It's a quantum mechanics thing. There's no really. It's not like a soccer ball. I don't think we can easily imagine it in our everyday life terms. But basically, there are properties of neutrons. There's a spin up and spin down. There's two states of the neutron, and they are equally probable in the normal neutron beam. But it's not really spinning, physically spinning. It's exactly, it interacts with, yeah. There's no charge involved in that, and I guess spin of neutron I probably should learn more on this, but I just know it precesses with the rotation. It precesses with the interaction of the magnetic field. Yes, please.
Some materials are activated by neutrons and being interactive. So when you do something like a piece of art or something, you radiate with neutrons, and you don't know what's inside it. How do you prevent it from becoming radioactive?
That's a good point, because once we work with museum objects, they are very hesitant to any new technology, and this is most of the time is new to those people. So to prevent it, we don't flush it with huge neutron beams from the beginning. So first of all, of course, there are some guesses what is inside. And not that many materials get activated. Some of them do. And what happens after absorption of neutron, they become radioactive, and they will become radioactive sometimes for a long time. But what we do first, we'll shine a small amount of neutrons, and then we'll look at what gamma rays coming out, for example. So we see what is being produced, and from that we can tell if we expose it to large amount of neutrons, will it get activated or not? And only after that we continue with the full measurement. But there's a big, of course there's a big question. Some of them cannot be used by neutrons because some materials get activated. Yes, please.
So a lot of the problems with sort of deploying this more widely, you alluded to in terms of having to bring the samples to the neutron source, or not being able to study things like strains on a bridge in situ and that kind of thing. Do you think is there sort of a path for development of technology that will enable this to be made more portable, or is that really not in the works?
I don't think in the near future, because the brightness of there are portable sources. You can buy commercial sources which are portable. They create neutrons of 14 MeV, for example, and 2 MeV neutrons, and then you can thermalize them. But the brightness of those sources is quite small. And if you want to look at strain, you really need a very short pulse. But once you get a very short pulse, the intensity becomes even lower. So for neutron imaging, it's challenging. But looking at the strain, and to measure strain, you really need to measure bright gauge position with high accuracy. You need good statistics. So it probably will be limited to the sources where you bring your sample into, but not to the field. But people talking about studying wood with portable sources and concrete. So some imaging can be done. And of course, they do a lot of gamma activation analysis. And for that, if it's not imaging, you still can do a lot of things. But when you need imaging, you have to spatially resolve the structure. It's probably still be done at the stationary sources. Thank you. Absorption contrast is very low, like in that case when the heart is imaged in the right picture here. So if you just do an absorption image looks like this. There is not much of a structure because absorption coefficient doesn't change much. But what changes is the refraction coefficient or phase changes of the photon. And then they now can use a phase contrast imaging, which is a bit more challenging than just transmission. But we'll do the same thing with neutrons. Now, X-ray radiography and tomography, I'll mention tomography as well, is well developed by now. There are a lot of instruments, a lot of techniques are done. And sources very bright, they exist around the world. They're lab sources, they're synchrotrons. They're very, very bright. So why would we add neutrons? And what neutrons bring to this field of imaging? And I'll try to show you what is unique with neutrons and why we use them. So first of all, neutrons and X-rays have completely different interaction with matter. So X-rays interact with electrons in the atom. As they propagate through the matter, they interact with electrons, and there's more electrons in a particular sample, there's more interaction, more absorption, more scattering, and so on. But neutrons don't interact with electrons. They interact with nucleus. And that's why the absorption contrast is very different for different materials. So what I'm showing here is a cross-section. So the diameter of each of those spheres proportional to the probability of neutron or X-ray to be absorbed. So the green ones are for X-rays and red for the neutrons. And as you can see, for hydrogen, for example, which is the lightest element, X-rays have almost no interaction because there is only one electron. But neutrons have the highest probability to absorb with hydrogen. And at the same time, look at iron, which is on the right-hand side. X-rays can interact with iron very heavily, very strongly, and get absorbed very easily, or scattered. But the neutrons can penetrate iron, and quite thick amount of it, and still can see hydrogen within an iron cask. So one of the demonstration images, which was done in the beginning, they took a lead bucket and put flour inside of the lead bucket and imaged that flour within the lead bucket with neutrons. Of course, X-rays are completely blocked by lead. So that's why neutrons can bring you some new possibilities and can be additional techniques for studies where X-rays cannot be helpful. And other atoms like deuterium and oxygen, aluminum, silicon are shown here. So you can see it again. The contrast mechanism is very different. And
I'd like to introduce Dr. Anton Tremsin, originally from Russia, and then spent some time in my home country, the UK, at the University of Leicester. and he's now up at the Space Sciences Lab up on the hill. Again, if those of you who come to Cal Day, they do a great tour up there next April. I'm sure that they'll be showing people around the labs up there again. But Dr. Tremsin has kindly brought some of the work that he's been doing up there at Space Sciences Lab down here to campus to tell us about this morning, and he's going to tell us about the interesting new things that we can do with neutron imaging. So, thanks, Anton.
Thank you. Good morning. So I would like to tell you something about the work we do at Space Sciences Lab, but not our main kind of work, because of course Space Sciences Lab is mostly about astrophysics and instrumentation and measurements, but I'll tell you about something of our main path. I will be talking about neutron imaging. And the reason I present you this is because we had some technology which we developed for astrophysical instrumentation. And then we extended it to neutron imaging. And I would like to convince you that you can indeed see a flower for a granite wall. So the neutrons have very specific features and capabilities. So in the talk, I'll briefly explain you and compare neutron imaging with X-ray imaging, because these are two complementary techniques. And most of you, of course, are familiar with X-ray radiography, but not many know about how neutrons are used for imaging. And then talk about contrast in transmission images, sources which you would use for neutron imaging, and show you how we contributed to that field, and then show some applications of neutron imaging in different branches of science. So, of course, many of you are familiar with X-ray radiography, and that's the technology which is used for many years since discovery of X-ray by Röntgen. And X-rays can penetrate quite thick objects, and we're all familiar with the applications in medical imaging. So basically, you have a source somewhere and a detector, and an object is between source and detector. You measure the photons which are absorbed by the detector, and you obtain an image. And the soft tissue usually is quite transparent, and heavy Z elements are opaque. So what the contrast in X-ray imaging is provided by the difference in absorption of X-rays. And the same thing will be with neutrons, but we'll have very different contrast mechanisms. So as is pointed out here, light elements like carbon, hydrogen, oxygen, which is consistency of most of our tissue, are quite transparent. But the heavy Z elements are opaque. So the heavier the element, the larger is absorption. And of course, X-rays are used in many other fields in addition to medical imaging, in non-destructive testing, and industry. And you can see inside of a particular connector, you can see the defects in that. Airplane turbines are inspected. So this is the technology which is well developed by now. One of the things where X-rays are used is in art, and the reason I mention this is because we use neutrons for art studies as well. So in that particular painting, you can see that the underlayer of the painting depicts that the man was in a hat, and there was no beard in it. But what you see on the surface now is this painting. So you have a means of non-destructively discovering what is underneath and how this painting was developed and painted, maybe altered at certain time. But in addition to just normal absorption contrast, there are many other techniques in X-ray imaging, which we will also have for neutron. And in addition to just relying on absorption, basically you send a photon, it grows through the object, or it doesn't go, depending on the cross-section, and then you detect it with a detector. There are other techniques, and one of them is called dark field imaging, or refraction contrast imaging is another one, because there are some situations where